I'm in class. What do you want? What do you want? Mekala Shashikumar, inform your friends to join. Net is quite good, I think, now. Shashikumar Mekala, is it audible?
Yes,
Yes, sir. Yes,
yes,
sir.
Please ask your friends to join. I'll be starting. It's very easy. This is quite important. Okay, I'll start. We are discussing about torsion, the moment which causes twist, twisting action, twisting action of shaft along the longitudinal axis is called as twisting moment, and the shaft is said to be subjected to torque. So torsion in the sense it is also a moment. It is also moment, but this moment in the sense a force which makes the body to rotate. So torque is also a moment, but this moment produces a twisting action. Okay, when this twisting moment acts on the shaft is said to be under torsion. Okay, like this, like this. For example, you might have like if I hold, if I let me write. Okay, I'll take this. Okay, see if I consider the shaft like this, the shaft like this shaft, you can see I have to bend my four fingers, my forefinger, okay, my forefinger, my middle finger, my ring finger, and my small finger that is pinky, that I have to bend in the direction of torque. For example, if this is my torque T, I have to bend my four fingers in the direction of torque. I have to bend my four fingers. These four fingers in the direction of torque, and thumb gives the axis. Thumb gives the axis. This is the axis. It is generally indicated by double arrow. Thumb gives the direction of torque. In this case, you can see that the torque is acting in this direction. Torque is acting, it is in this direction. I have to bend my four fingers. You have to imagine like this. You have to imagine three-dimensionally. It is, I will write like it. Generally, the shaft, the what we are considering is circular cross section. Why we will discuss later. If I consider torque like this torque is acting like this T. And if I bend my four fingers in a direction, my thumb gives the axis, my thumb indicates the axis. If I apply now like this is acting like this, and my thumb gives the axis like this. Like this is in this case, it has to be uh, how this is this has to be like this in this direction. So when the torque is applied like this gives the direction. This is a right hand thumb rule. Time being, you don't worry about it. But what you should know is when you talk about bending moment, it is along z direction. If you bend your fingers in the direction of the bending moment, your axis will be like this. This is the axis. Whereas the torque, you assume that it is along x axis. You have to, this is according to right hand thumb rule, if you bend your four fingers in the direction of moment, the thumb gives the axis. So in this case also, I am bending my four fingers in the direction of torque. That my thumb is along x-axis. Whereas bending moment, if I bend my four fingers in the direction of bending moment, the thumb is in along z direction. Either it can be like this, then the z direction will be like this. Okay, which will be you will be getting clear as we solve the problems. Okay. Now that is what we should know. Now the moment, this is the moment which causes twisting action. This moment, when it applied to the beam, it causes bending moment. But it is now it is causing twisting action, and the shaft is subjected to torsion. Example can be example example your propeller shaft, motor shaft, okay, turbines. Many places we come across the shaft subjected to torsion, isn't it? If you rotate when you're bowling, okay, it acts like a bearing. For example, a friend is twisting your hand, then isn't it at your arm where the your at your shoulder is subjected to torque. Okay, you can imagine like that. Next, this is a bending moment. If I take bending moment, if I consider the cantilever beam like this, of circular cross section, bending moment is like this. Yeah, this is along, this is the bending moment, z direction. Torque is like this. Bending moment also double arrow. torque along x-axis. Okay. Next, before deriving the torque equation, we will make few assumptions, and I will explain this. Assumptions made in deriving torque equation. First, now let us consider a shaft, or the shaft which we are considering are of circular cross section. Why you will come to know now. Okay, this is the shaft. I have made few divisions of this. I have drawn few longitudinal lines. I have drawn the arcs that indicates that this shaft is of circular cross section. Okay. Now, when I subject this shaft to torsion, I will indicate a positive torque. This is my positive torque. When I subject the shaft to the torsion, the lines which I cannot draw straight is little difficult to draw in the tab. Okay. So what can you see from here is the lines which were longitudinal or horizontal have become helix or spiral, and the major thing what we inference is these circular cross sections which were circular remain circular only. It is just rotated about the axis, that is x-axis. Okay, it is not twisted. This circular cross section, okay, which were the these are the circular cross sections. These are circular cross sections. This circular cross section remains circular. Okay, this is one of the major assumptions. Assumptions are the what can you say, inference. Okay, when you take circular cross section, so when you say take circular cross section, when you apply the torque, circular cross section remains circular. Okay, and in another way we can say there is no warpage. You can, if you take rectangular or square or any other cross section, there will be a linear strain, and the circular cross section changes to some irregular shape. But when you say take circular cross section, there won't be any change in, there won't be any linear strain, and circular cross section remains circular. Let me write this in terms of points. You will come to know. First, plane section remain plane, that is cross section rotates about and remain perpendicular to longitudinal axis. Even though this cross section rotates, which was perpendicular like this, now also it remains perpendicular only. Now also this cross sections will be perpendicular to the longitudinal axis. It is just rotated about that axis. Okay, it will not move. It will not move like this cross section which was there. It will not move like this. This cross section will not move like this. Okay. Next, the distance between the cross section hold on the distance between the cross section remains constant during the twisting deformation. Okay, that is, there is no extension or contraction along longitudinal direction. Opaque conduction. The distance between the cross section, for example, before twisting, if it is 2 centimeters, after twisting also this distance 2 centimeter, 3 centimeter, the distance remains the same. It means to say that there is no strain along the longitudinal direction. Okay, and first point is circular cross section remains circular only like this. Okay, circular cross section remains circular, and then there is no linear strain. Okay, these 2 points. And then when I apply a torque, shear stresses are induced. Shear stresses, sorry, shear stresses are induced, which causes shear strain. Shear strains are of small small magnitude. That is, it is very small. Okay, these are the few assumptions. Is now few assumptions made while during the torsion equations. Okay, next, there is something called as pure torsion. Pure torsion. For example, let me write the sketch first. This is the positive torque convention T. So that if you hold your fingers in this direction, your thumb will be like this, and if in this direction, your thumb will be like this, pointing like this. Okay, this is positive torque. True torsion in the sense, if I apply, you have to imagine like this. You have to always imagine like this. This is my shaft. I have applied a torque T. So throughout the length of the shaft, the torque remains the constant of same magnitude T only. This is called as true torsion. Okay, let me write it. All cross section of the shaft are subjected to same internal torque T. Therefore, the shaft is said to be subjected to pure torsion. Throughout the length of the shaft, internal torque or the torque remains the same, okay, of same magnitude, and hence the shaft is said to be under pure torsion. By assuming this, we'll come to few conclusion which we'll discuss later. Next, if this derivation doesn't complete, I will take I will extend for another 20 minutes. I will schedule one more class. Okay. Now I will consider derivation of torsion equation. I will consider a shaft of length L in which for steady I will take a small length dx. This length I'll cut it and take. This is subjected to torsion T. This is subjected to torsion T. When I take this, when I exaggerate this, this is of length dx. I will take few points for study. This is point A, point B, connect it, point C, point D. Now tell me, when I apply a torque, this will take a new position like this. This will take a new position. Sorry, this will take a new position like this. This I will call it as B dash, and this I will call it as D dash. The radius remains the same. This is of radius R. If I take radius R, this is the radius R. This, whatever the deformation which has happened, this deformation is d phi. This is called as angle of twist, rate of angle of twist. In this case, this is angle of twist, d phi. The small angle, this is b dash. Don't worry, this is b dash. This angle of twist, I've indicated it as d phi. Okay, is this clear? No. Now, what is the inference from this? Now, this was actually 90 degree. This before applying the torque, this was 90 degree. This was 90 degree. When you consider a body like this, when do you say there is a change in angle? Now 90 degree has changed to some angle, isn't it? A, B, C, D, C dash, D dash. Before this is on 90 degree, now it has changed to some angle. This D, this has changed to some angle. How this will happen? When I subject this to shear stress, when I subject this to shear stress only, this will happen. So it means to say that when I apply a torque, the shaft is subjected to shear stresses only, pure shear stress. It is under the condition of pure shear stress, and also whatever that sine cosine term, that is maximum principal stress, minimum principal stress, all everything holds good. This is like under pure shear stress condition. Pure shear stress condition. Okay, there is no axial loads, there is no axial strains induced. It is under pure shear stress condition. Okay. Now let me write the angles of the element are no longer equal to 90 degree. The element is therefore in pure share, which means which means element is subjected to shear strain but not normal strain. When is subjected to shear stress, it is subjected to shear strain. There is no normal strain. Okay. Now, from this figure, uh, we have written gamma is equal to, in this case, gamma is equal to, if this is cc dash divided by, if this is length dx or dl, we have written dx. Similarly, in this case, I can write shear strain gamma max, or this is a maximum shear strain gamma max, gamma max, which should be equal to this this angle, this, what is this, this length, this is the change in angle. In this case this is cc dash, in this case this is bb dash divided by length dx. Can I write it as bb dash by dx, bb dash by dx, isn't it? This is bb dash, this is bb dash by length, it is dx, by length dx. Similarly, cc dash by dx, it was cc dash, change in length by original length, you cc dash by dx. In this case bb dash by dx. Okay, but we also know that arc length s is equal to r theta. Similarly, by using arc length s is equal to r theta, length, the arc length r is r only, theta is d phi. I am expressing bb dash in terms of this r and d phi. This angle is d phi, r into d phi, r into d phi. Okay. Now let me write gamma max, gamma max, which is equal to r into d phi by dx. Okay, where d phi, d phi by dx is called as rate of angle of twist or angle of twist per unit length, angle of twist per unit length. Generally, this is indicated by theta. Theta is equal to d phi by dx, or I can write gamma max, which is equal to r into theta. Okay. Now, gamma max is equal to r into theta. We are discussing a special case of torsion called as pure torsion. What happens in case of pure torsion? In the sense, in the special case of pure torsion, I'll explain this. The angle of twist is equal to total angle of twist phi divided by the total length L. Therefore, it means to say that for pure torsion, theta, which was given by rate of change of angle of twist by unit length, becomes theta is equal to angle, total angle of twist by total length L. Theta is equal to phi by L. Okay. For pure torsion, this becomes theta is equal to phi by L. Okay. Next. Is it clear? In the case of special pure torsion, the angle of twist is equal to total angle of twist pi divided by the total length L. That is theta, which was change in angle of twist per unit length, now become equal to theta is equal to pi by L. Okay, I have left it 10 minutes. I'll schedule one more link. I'll schedule one more link and we'll continue. Okay. Or gamma, which was gamma max, which is equal to r theta. Let me write gamma max, which is equal to r into pi by L. Okay, r into pi by L. Next, next, uh, this was my shaft. I have taken, I have not taken the complete radius of the shaft. I have taken the inner core of the shaft. Assume this is the actual radius r. This is the actual radius r. I have taken a small radius of length rho. This is length rho. Now the same thing holds good. This A, B, C, D, when it deforms, this deforms to B dash, and this deforms to D dash, which was actually AB. I cannot write here, but try to understand. So what I'm trying to tell you is this whatever what we got, gamma max is equal to r pi by L. Gamma max is equal to r pi by L, where r is the maximum radius. Instead of maximum radius, if I take any other radius from 0 to r, for example, any radius rose, for example, if the radius is from 0 to 10 centimeter, if I take 4 centimeter also, this relation r pi by L holds good. Rho instead of r, this rho pi by L holds good. So how this gamma max is then? Gamma max is something like some, this is like this, gamma max is equal to, I can write in like same thing, like this is some function x into some, I can write like this, gamma max, which is equal to mm, r phi by L, r, I can write like this. We know that gamma max is equal to r theta, okay, uh, and then theta, give me a moment. Okay, gamma max is equal to r theta. Okay, here I can write, give me a moment. Gamma max r pi by L. Okay, okay. Gamma max is equal to r into theta. R, like, this is not gamma. This is gamma max is equal to r phi by L. But if I take any radius other than radius r, this gamma will be. This is not gamma max. This is other than any other radius other than r, this is only rho pi by L. This is not the maximum strain. This is some strain which is varying rho pi by L. Okay. Now I can write. Now I can write. Uh, Gamma is equal to. Give me a moment. Sorry, gamma max, gamma which is equal to any other radius is equal to rho phi by L. Okay. Now I can write. Now I can write. Uh, mm, can you tell me how I can write? Mm, okay. This gamma I can write it as rho into phi by L is theta, or I can write gamma max by R is equal to theta. Or I can write gamma is equal to rho into gamma max by R. Gamma max, gamma max by R. So it means to say that gamma is equal to some x into gamma max by R. So what does it mean? My shear strain is varying linearly. Shear strain is varying linearly because the factor 0 to r gesture is varying linearly. 0 to r came into picture, for example, from 0 to 10 centimeter, depending upon 2, 3, 4, 5 centimeter, whatever it choose. This instead of the rho, I can write it as x, which is nothing gamma is equal to gamma max by r. Okay. Now, for example, okay, hope you understood this. Gamma is equal to x into gamma max by r, or I can write gamma is equal to rho in, which is nothing but rho into gamma max by r. Or you can say when r becomes in rho, because radius becomes r, this gamma which is equal to gamma max. When at the inner fiber, when radius is equal to 0, gamma will become equal to 0. Therefore, shear tends very linearly from 0 to maximum. That you should keep it in mind. Okay. Next, next, uh, after this, after this, I have applied a torque like this. This is the positive torque. I have applied a torque like this. If I take a suction like this, if I take any section or surface of the shaft, this torque is pulling like this. This torque is like this. Therefore, the shear stresses tau will be like this. This will be like this. This will be on the upper surface. It will be it will be like this, like this. Lower surface it will be like this. So if I exaggerate and write, this is the surface of the shaft, this is toe acting like this is like this will be like this will be like this. Hope you can understand this. Okay. Now, from Hooke's law, last 1 minute remaining. Okay, I will not continue. I'll schedule the link. As soon as you get the link, you join.